Hello students, we're going to go over questions 49 and 50 from the book. Question 49, there's a picture that goes with question 49, it's figure 66. A stone of mass 0.25 kilograms attached to the end of a string is moving in a vertical circle with a radius of 0.8 meters at a constant speed. The string will break if the tension is more than 10 newtons. Explain whether the string is more likely to break when the stone passes the lowest point. Or the highest point. So because the stone is going in a vertical circle, we have to take into account the weight. Weight is represented as mg. Mg is the red arrow, and it's always down. It never is in any direction other than down. But the centripetal force is represented by the blue arrows. Now the blue arrows in this diagram are all the same length, so because the object is going at a constant speed, the centripetal force must always be the same. The tension, however, is not always the same. The tension could actually be zero at top. Think about if something is going in a circle in a vertical, as it's going over the top, it doesn't need as much tension to bring it back down because it's got weight helping it. At the bottom, the weight is actually pulling on the string more than it would be at the top. So the tension at the bottom would be the greatest. So tension at the bottom is the greatest. It's greater than the sides. There's still some tensions on the sides, and the tension is the smallest at the top because, again, gravity and weight is helping the object move in a circle. So as it reaches the top, that gravitational force is pulling down. So it's kind of confusing because if you look at the blue arrow represents the centripetal force, but it doesn't represent the tension. So the tension in the string is equal to the tension up plus mg. So look at this bottom tension here. Because the red arrow is down, it's pulling on the string more. And the string is down. So when you're looking at the top, the string can't be pulling down. The string is pulling down, but the weight can't be pulling the string down because of the way the string is positioned. So the weight actually helps make it so that there's less tension required. All right. I've shown some work here. So the centripetal force is equal to the mass times the gravity. The mass times the... so at the top, if you consider at the top that there doesn't need to be any tension, just the gravitational force is the centripetal force. So you've got centripetal force equals 2.45. And then you can put your equation here for centripetal force. 2.45 equals the mass times the centripetal acceleration. 7.8 equals v squared. Don't forget the square root when you're trying to find your answer. I also figured out halfway through that you could just use this equation. You could say that the centripetal acceleration is equal to gravity. But I like to use centripetal force because I like to think about all of the forces acting on the objects. For the second part, it says, what is the maximum speed if the tension can only be 10 newtons? Okay, so we use our equation. So we use our equation here that says the tension in the string is the centripetal force up plus the mg. So if the maximum tension is 10, we'll put in 10 here. Then we'll put in our centripetal force equation here, and then we'll put in our weight equation here. Once you solve for v squared, you get 4.9. Now that makes sense because this the speed was 2.8, so you can't be going too much faster than 2.8, right? You definitely can't be going less than 2.8. You wouldn't think you would be going less than 2.8. But 4.9 sounds good. Okay. The next question, number 50. A car is of mass this is going over a hill. Create an expression in terms of mvr that describes the normal force. So here's the picture. Now the picture is interesting. The thing you need to understand about the picture is that when you're driving in a car and you go over a hill, you do feel like you're lighter because the car wants to keep on going straight. The car wants to go in a straight line, but the hill is curved. So when you're going in a straight line and you start to reach the top of the hill, the car wants to just stay at the top of the hill. So you feel lighter. If you feel lighter, there's less normal force. There's less normal force at the top of the hill. Okay, so if there's less normal force, what's the equation we can create here? Now this picture is actually kind of difficult to explain and draw, but I think if we just keep in mind that there's less normal force when you're at the top of the hill, you're in good shape. Okay. So the normal force is equal to the mg minus the centripetal force. The centripetal force is what causes it to go in a circle, and the mg is helping that go into a circle. But if the mg equals the centripetal force, then you'll feel like the car is getting air, or you'll feel weightless in the car. And some people have experienced this when they're going really, really fast. So my equation says Fn equals mg minus Fc, and then it says put in terms of mvr. I added g. It doesn't say to put g in the question, but I think it should. And then I factored out the m here. So then the Fn is equal to m times the parentheses g minus v squared over r. Okay, so we've got our equation. We've got all these givens: 60 Newton or 60 meters for the radius, 1,400 kilograms, 50 kilometers per hour, which needs to be converted to 13.9 meters per second. And then mg. Mg is the weight, so I just put that in there as 13,734. We know that our centripetal force must be equal to 4,501 because we have the speed. So if we have the speed, we know what the centripetal force is. If the centripetal force is 4,501, we can solve for Fn by just plugging in the weight here for mg and then solving for Fn. Now Fn should be less because if you're going up the hill, you're pushing on the ground less, the car wants to go up. Now, there's no force pulling the car up, but it's just, you need to just think of it as when you go over a hill, you feel lighter. So the weight is being used as centripetal force in a way. So the weight is helping it maintain that circle. The more the car weighs, the more it will stay in that circular path. If the car is very light and you go very fast, you'll definitely be feeling some air or some weightlessness as you go over that hill. And you see this in movies and things like that. You shouldn't try this on the road because it could be bad for your car. And you know, if you lose contact with the road, you lose control. You have no traction. You have no friction. You can't turn. You're just basically a projectile at that point. All right. So I've left all my work here so that you can take a look and compare that to your work.